Have you ever been driving past a power plant or some huge factory and seen those enormous curved structures just dominating the skyline? You know exactly the ones I'm talking about. They look like they're straight out of a sci-fi movie, but their real job is actually one of the most important and, frankly, one of the coolest in all of modern industry. Yep, these bad boys right here, the classic hyperboloid cooling tower. And you always see that huge white plume just billowing out at the top. It's a sight we all know, but what are we actually looking at? The first thing most people think is that smoke? Is it pollution? I mean, it's coming from a big industrial site, right? It's got to be bad for the environment. It's probably the #1 question people have. Well, the answer might actually surprise you. Nope. It's almost entirely clean water vapor. It's basically just steam. See, a cooling tower's main job isn't to pollute anything. Its purpose is to get rid of absolutely massive amounts of waste heat. Think of it as a giant radiator for our industrial world. Okay, so to really get our heads around these things, we're going to break it all down. First, we'll talk about why they're so ridiculously important. Then, we're going to peek inside what I like to call the rain machine. After that, we'll get into the actual science of cooling and how it's measured, check out all the different types of towers, and finally, see how engineers squeeze every last drop of performance out of them. So let's start with their #1 job. Just think about it for a second. Our entire modern world runs hot. Power plants, chemical refineries, you name it, they all generate a staggering amount of waste heat. And you can't just let that stuff build up. Getting rid of it is a massive fundamental challenge. And these towers, they're the workhorses that get it done. So how in the world do you get rid of that much heat? Well, the answer is both incredibly simple and amazingly powerful. You use water. It all comes down to the magic of evaporative cooling. Okay, check out this diagram. It's really just a big, continuous cycle. You've got hot water from the plant, right? It gets pumped into the cooling tower. Inside, it gets cooled way down. That newly chilled water is then collected and pumped right back to the plant to go soak up more heat. It's a simple, elegant, and totally closed loop. Honestly, the best way to think about it is this. A cooling tower is basically a giant sweat gland for a power plant. It's the same principle. When we get hot, our bodies release sweat. The evaporation of that sweat from our skin is what cools us down. These towers do the exact same thing, just on an absolutely epic scale. So here's how that sweating actually works, in 4 easy steps. First, the hot water is sprayed over this special material called fill, which is designed to create a massive surface area. Think thousands of tiny surfaces. Second, huge fans pull air through that curtain of falling water. Third, and this is the magic moment, a tiny bit of that water evaporates. As it turns into vapor, it literally sucks a ton of heat energy out of the water that's left. And finally, that much, much cooler water collects in a basin at the bottom, ready to be sent back to do its job all over again. Now, what's really fascinating is how you know if a tower is actually doing its job well. It's not just a guessing game. There's a really precise science to it, and it all boils down to a couple of key measurements. This visual right here tells you pretty much everything you need to know. Performance is all about the relationship between a few key temperatures. You've got the hot water going in, the cold water coming out, and something called the wet bulb temperature of the air. This gives us our 2 critical metrics, range and approach. First up, we have range. Super simple. It's just the temperature drop, the difference between the hot water going in and the cold water coming out. But here's the kicker, and this is important. The tower itself doesn't decide its own range. The power plant does. The plant sets the heat load, and the tower's job is just to handle whatever's thrown at it. And this quote from Brentwood Industries really hits the nail on the head. So many people get this wrong. Range tells you about the job the tower has to do, but approach tells you how well the tower is actually doing that job. So the real MVP, the true measure of performance, is approach. Now, to get this, we have to talk about wet bulb temperature. It sounds super technical, but just think of it like this. On any given day, it's the perfect score for cooling. It's the absolute coldest that water can possibly get just through evaporation. Approach is simply how close the tower gets to that perfect score. So a smaller approach means your tower is an A-plus student. Now, getting that small approach, that A-plus score, is not easy, and a whole lot of it comes down to design, because not every cooling job is the same, not by a long shot. So engineers have come up with all different kinds of towers for every possible task. The biggest difference you'll see is how they move the air. Those giant hyperbolic towers we all recognize, those are natural draft towers. Their insane height creates a chimney effect. Hot, steamy air naturally rises and pulls cool air in from the bottom. But most other towers are mechanical draft. They use massive fans to literally force the air through, which makes them way more compact and versatile. And the design choices go even deeper. This slide shows the two main ways that the air and water can actually meet. On the left, you've got counterflow, where the air moves straight up, directly opposing the falling water. On the right is crossflow, where the air comes in from the side, moving horizontally through the water. Now, counterflow is usually a bit more efficient, but the crossflow design can be cheaper to build and easier to maintain. It's all about trade-offs. And get this, even the fill material inside the tower makes a huge difference. Older towers use something called splash fill, which basically just breaks the water into droplets. But modern film fill, which spreads the water into a super thin sheet, is way, way more efficient. Just look at this data. It needs less pump power and way less air to get the same job done. We're talking major energy savings. So all of these design choices, the fans, the flow, the fill, it's all about one thing, efficiency. Because in the world of industrial cooling, every single degree of temperature, every kilowatt of power translates directly into real-world savings of energy, water, and of course, money. So keeping these towers running at peak performance is a constant battle. The opportunities for saving energy, as you can see here, are just massive. It really comes down to a few key things: tuning the airflow, managing the water flow by keeping everything clean and balanced, and even carefully controlling the water chemistry. A single upgrade, like just switching to modern fan blades, can cut the energy for the fan by up to 30%. And the impact of that efficiency is just staggering. For a big thermal power plant, getting the cooling water just 1 single degree Celsius cooler means the whole plant needs less fuel to make the same amount of electricity. That's a huge efficiency gain that, when you think about it across an entire power grid, saves an unbelievable amount of energy and money. So I want to leave you with this one thought. The next time you're driving down the highway and you see one of these unsung giants on the horizon, are you going to see a smokestack, or are you going to see a massive, finely tuned rain machine, an incredible piece of engineering working tirelessly to keep our entire modern world running and cool?